Hello, this is Stuart Mason from Math 156/E156 with script 8C. We're talking about the efficiency of estimators and how bias affects that. So let's take a look at a number of different estimators for beta in a uniform between 0 and some upper bound. We know that the sample mean and median both have expectation beta over 2. So twice of either of them will have an expectation of beta, meaning it's unbiased because its expected value is equal to the true value of the parameter. And we can also unbias the maximum being our MLE estimator. We can unbias it to obtain an unbiased estimator, and we'll prove it in the math notes. You can also add the minimum to the maximum, and that will also unbias it, which kind of makes sense, right? As near as you get to the lower end would be about you'd expect to be how far you are from the upper end with your max estimate. And then also we can do what's basically a method of moments by using the standard deviation. So this uses the first and second moments, essentially to beta over square root 12. So now the question is, which of these estimators has the smallest variance? So let's 1,000 times, let's draw 25 samples from our distribution and compute each of these estimators. So we'll look at the average and spread of each of them. That was the means. Now the medians. The median is centered in a similar place, but you see it tends to be much more variable. The max we know is centered at the true value because we unbiased it, and the variance is much lower, so that's even better. And then the min plus max is also quite good, although its variance is a little higher. And our standard deviation does better than the mean or median, but we know it's biased. Let's see what's going on. So we can tell that we want 2 rows of 3 columns of plots and look at histograms for each of these estimators. Let's make this a little bigger. You can see the mean and median are both centered right at 12 like we'd expect because they're not biased, but they're kind of widely spread. The median we saw had a higher variance, and we can also see that in this picture, right? It ranges from 5 to 20, whereas the mean only ranges from 8 to 18. The max we've unbiased, and it's also much tighter, right? It really only has any appreciable mass down to like 11. Min-max becomes a little more normal looking than the max, but it's still, its variance is a little higher and it's worse. And the standard deviation is slightly biased and also has a kind of a widespread. So let's turn the plots back to normal. Now the mean square error, which we've seen in the notes, combines bias and efficiency, and it works out to be the variance of the estimator plus the bias of the estimator squared. So for our unbiased estimators, this is just going to be the variance because the bias is 0. So now let's talk about cases where efficiency is better than a purely unbiased estimator. So suppose we have X successes in 16 trials. What is the probability P of success? So X over N is the MLE, and it's unbiased. But it has high mean square error for P's near 0 and 1. I think this is called the continuity problem. If we add an arbitrary number of successes and trials, then we are biasing the statistic in favor of the P that we're essentially adding, but also reducing its variance by doing that. In this case, we're basically adding 1 success and 2 trials, so we're biasing the variance to be closer to a half, but this will also have the effect of lowering the variance. And there's all kinds of messy algebra around this in the notes in the textbook, but we basically come up with this as the mean square error in the general case, where we add S successes and T trials. Let's make our code window a little bigger. So for 16 trials, let's look at the mean square error where we don't bias the statistic at all. So if the probability are 0 and 1, then our estimate will be perfect, which kind of makes sense. If the probability something is 0, you'll have 0 successes, you'll estimate it to be 0%. If the probability is 1, you will have n successes, you'll estimate the probability to be 1. And then as we get closer and closer to a half, the variance gets higher and higher, and so the mean square error gets higher and higher. Now let's set s equal to 1 and t equal to 2. Now this has the effect of biasing our estimator in favor of 1/2. If our data come out with a p close to 0, adding 1 success in 2 trials will make our p bigger. If we come up with a p greater than 1/2, closer to 1, then adding 1 success but 2 trials will make the whole thing smaller. This really nicely illustrates the trade-off between bias and variance. We have biased the statistic, so we've added error where previously we had none. But by biasing it, we've reduced the variance. So now let's take a look at Paul's example. So a rookie with a true probability of hitting bats 16 times in spring training. So Paul is basically saying these are all possible probabilities of observing different values, and then he's weighting them by what the p we would observe, what the p we would calculate would be, and showing that that works out to be exactly p, and this calculation yields the variance for that estimator. And of course, if there's no bias, the variance and mean square error are the same thing. But what if we basically apply this correction from the previous example, and we'll always add 1 success and 18 at-bats? In that case, the expected value of our estimate is 0.32. So this overestimate is due to the biasing it in favor of being closer to 1/2. And the theoretical expectation works out the same. But the variance is reduced, and it's reduced by a value which is greater than the bias we've introduced to the estimator. And that means that it's going to have a smaller mean squared error. Paul points out that we do even better if instead of biasing it in favor of 1/2, we bias it in favor of 1/3. The reason for that is because this is closer to the true value of p. So we add the curve here, and you see that closer to 0, the bias we've introduced is not as bad. And then it's also asymmetrical now, because if the true value is closer to 1, then by biasing in favor of 1/3, we are doing worse to our estimate than we are if it's 0 biasing it closer to 1/3, whereas in the half case, everything was perfectly symmetrical. And Paul once again goes through and shows the expectations and variance, and then he says if we press this idea further, we'll reinvent Bayesian statistics. And he's right? We could imagine having some prior guess about what p is, which is essentially what these biases would be, right? If we had reason to think it was 1/2, we might bias our data in favor of 1/2. If we had reason to think it was 1/3, etc. And so that's an idea that we'll explore a little further in subsequent weeks. But for now, I hope now you understand a little better the trade-off between bias and inefficiency, and why bias is not always a bad thing. Great, I hope this was helpful, and I'll see you guys on Wednesday.